So IUDX stands for India Urban Data Exchange, and together IUDX and CSP are actually part of project Data Kaveri, and the general aim is to facilitate public data for public good. India Urban Data Exchange is actually a collaborative initiative between Smart Cities Mission India through the Ministry of Housing and Urban Affairs and Indian Institute of Science, Bangalore. Essentially, it is an open source data exchange platform that facilitates secure, authenticated, and managed exchange of data amongst various stakeholders, which are generally data providers and consumers. We are currently live and we are deployed in dozen cities in India, and more cities are joining us by the day, and hence we will have a lot of data with us, and there's a lot more emphasis on the usage of the data, and that brings us to that is why this series we feel is coming at the right time. This series is going to be, we hope that this will be facilitating a lot of discussions around the advances in the data space. So we hope to cover topics like data privacy and security, data policies, and also the use cases around this data, how various data sources can be used to put out exciting use cases which will be useful. So some of the talks that we are going to hope that in data privacy and security, like we are hoping that we will get talks from the areas such as differential privacy, secure multi-party compute, enclaves, all these things which will allow essentially a better usage of the data that we are providing, while also covering the privacy aspects of the data. With that, let me please allow me to welcome Professor Sanjay Ranka, who is our speaker today. Sanjay is a distinguished professor in Department of Computer Information and Science at University of Florida. He has also served as CTO at Paramark during 1999 to 2002, and Paramark was a highly successful internet company. His research interests are in the area of high-performance computing and big data science, and the current focus is in the development of efficient computational methods and data analysis techniques to model scientific phenomena. And the practical applications that are being focused right now in the area of healthcare improvement and reducing traffic incidents. He's a prolific author with over 300 plus journals. He's co-authored a book, many monographs. He's a fellow IEEE AAAS and AAIA. And amongst many other achievements, he recently won the 2020 Research Impact Award from IEEE Technical Committee on Cloud Computing. He's an associate editor-in-chief of Journals of Parallel and Distributed Computing, and an associate editor of ACM Computing Surveys, IEEE ACM Transactions on Computational Biology and Bioinformatics, International Journal of Computing. Today, the title of his talk is Leveraging AI for Smart Transportation. And from the perspective of IUDX team, I think I'm really looking forward to it, because ITMS data is one of the very consistent data, one of the key and consistent data sources that is available from some cities on IUDX platform today. So I think without further delay, I would now once again welcome Professor Sanjay Ranka, and I will turn it over to him. Just one quick comment before that. There will be a detailed Q&A session at the end of the talk, and in case during the talk you have some query, please use the raise hand feature, and I think Stefan will moderate and hand it over to Professor Sanjay. Any questions? So with that, welcome Professor Sanjay, and over to you now.
Thank you very much. Can you see my screen and my PowerPoint slide?
Yes, we can.
Okay, wonderful. Well, thank you for the kind introduction. I'm Sanjay Ranka. I'm a faculty in computer science at University of Florida. This work is supported by a variety of agencies. Chief among them, National Science Foundation has a Smart Cities program. Also, A lot of work is supported by Florida Department of Transportation at a state level, and the District 5 basically represents City of Orlando, and we also work with City of Gainesville, where University of Florida is located. So I'd like to thank all these people who have been both participants and collaborators in this research. The team consists of a number of PhD students on the left, mostly computer science students. Many of them have graduated at this juncture, a couple of faculty from computer science, and then we also have a variety of domain expertise coming from civil engineering department who work on transportation applications. Um, why AI in transportation and why now? As you are probably aware, that things have rapidly changed in the world of both data collection because the sensors have become more accurate. Pretty much at this juncture, everyone carries a high resolution camera on their phones, which would have costed hundreds of dollars or even thousands of dollars only 10 years ago. And the cost of computing and resources have dramatically gone down over the last decade or so. And along with that has come improvements in machine learning algorithms. Combined together, it has enabled a variety of applications, and clearly transportation and logistics are expected, as you can see on the right-hand side, to be a good potential target for applying these applications. Most of you are familiar with machine learning. I'll just give a very quick overview. At a very simple level, what machine learning or AI tends to do is have, especially the data-driven methods, you have, as for example, a lot of images, and you're trying to figure out which class it belongs to. Then you have, say, thousands of such images. Then generally there is a convolution layer followed by some form of pooling in a fully connected layer. And the idea is that this machine is supposed to, given input-output combinations, be able to learn to classify whether an image consists of one of these 5 types of objects. And obviously one can create a 6th category, which is basically would be that none of them exist, right? Just like anything else, what you do is you try to make sure that you train the machine on a training set. You can fine tune your models, parameters, etc., the size of the network, etc. And then you test it and see whether the machine actually learned something or just remembered the stuff by rote. Remember that these deep neural networks and other networks which are popular today have a large number of parameters, so it's easy for them to remember everything by rote, and you want to make sure that they can actually generalize by looking at a set which they have not seen before. What we try to do is try to apply AI to target applications in transportation. In the middle, you can see that we use a variety of sensors like video, radar. You will see some information on ground sensors. LiDAR is becoming more popular now. And also many of the intersections which we have right now operational in the city of Gainesville also have roadside units which can communicate with cars which are passing by. So we want to be able to do 2 things at a broad level. Improve signal timing so that traffic can move more smoothly throughout the day. I'm sure you're familiar with traffic jams being in Bangalore and other cities in India. Our goal is to be able to minimize the wait time or improve the travel time on a corridor or a network itself. And the other important part is that a large number of accidents, and many of them fatal, happen at the intersections themselves. Our goal is to be able to analyze the intersection both from a design perspective, but also from a signal timing and a perspective on see how safe they are, and by looking at the data which is coming in. But more importantly, also in the future, as vehicles become more and more connected, the infrastructure being smart can then send information or presence of pedestrians or abnormal behavior to all the vehicles on the intersection to prevent accidents from happening. So these are our 2 main goals. And I'm going to talk about a variety of techniques which we are using for both data collection, processing, and then how do you then use machine learning to be able to solve the end-to-end application. So What are the requirements for application of AI in transportation? And I heard a nice introduction of your institute and what you're trying to do, but at a high level, you're collecting data for some end goal, and we do the same. We have data coming from a transportation infrastructure, some of it in real time, and some of it in offline mode. We need that to be able to test our algorithms and make sure they work in the real world. We need a large amount of computational and storage infrastructure. We do both computing on the edge, as you will see, as well as store a large amount of data on the cloud to get a perspective of the entire city. So, for example, you may do some computing on the edge at an intersection. By effectively doing that, you compress the data, and then you get a vignette of the entire city by collecting the data from every intersection, and you have now what's going on in the entire city.
Sanjay, I have a question from Abhay.
Sure. Go ahead.
Yeah, I just wanted clarification on the data sources because I just thought that will help in understanding the talk. So this radar is like the millimeter wave radar?
It is millimeter wave radar, and I don't have all the details with me right now, but I can probably send them to you.
But then it is like what it is orchestrated right on that intersection that we are.
Correct. But what you will see today, most of my work is on video processing and using sensor data. Although we do use radar for seeing long distance and especially in the nighttime, where sometimes the video is not particularly great.
Okay. And this, what is this ground sensor? Is this like something which is for?
I will clarify that in a few minutes.
Sure. Thanks.
Okay. Yeah. So now you have all these data sets, but an important part of AI is to be able to also have a lot of similar data. In particular, there are scenarios in the real world which you cannot always create, right? So, for example, there's a signal timing plan on a particular intersection. You can't just go and change it as many times as you want. Traffic engineers are not going to allow you to do that, or some crazy plans which they've not seen before. You want to be able to simulate that to create counterfactuals. So in a lot of ways, AI is not only about learning what exists today, but also be able to learn what doesn't exist today, both from an optimization point of view and also minimizing mistakes. So we have a large simulator infrastructure along with the real data. And then, of course, we use the standard tools which are publicly available along with our own algorithms, techniques which are based on GANs, deep neural networks, semantic segmentation, and the likes. So what it also shows you is that, look, it's not only about collecting the data, but it's all about being able to process large amounts of data and feeding it to a machine learning algorithm and then using the results of that. There's an interplay which is, if you may, circular in nature, as you'll see later, for you to be able to solve real world applications. So let me tell you a little bit more details about the transportation infrastructure which we have in place. In the middle, you can see this is University of Florida and City of Gainesville, and we have 27 intersections, roughly over 4 corridors of total perimeter length, maybe around 12 to 15 kilometers. And we get real-time data from all these 27 of them. Also, there are roadside units on all of these which can interact with vehicles. Obviously, the number of vehicles which they can interact with right now are very limited. We have installed 60 OBUs and buses and public vehicles, and they interact with them all the time. So we want to be able to use that and then be able to also collect data from fisheye cameras from all these intersections. So with that in mind, and all of these intersections are also connected by a fiber optic link to the servers in City of Gainesville, and we have a direct feed from those servers. So we can get this data in reasonably real time with a very limited latency. But our goal is obviously to have data beyond that. We also get data from around 400 intersections from City of Orlando, which gives us, this is mostly offline data, and combined together, we have collected roughly 50 terabytes of data over 400 intersections or so over the last couple of years. We have developed a computation and storage infrastructure where we process, if you may, have a version of edge computing sitting in city of Gainesville, where all the high bandwidth data, like for example, video data, is processed on the GPU right there, and then sent into the cloud. Some of the data is very small and infrequent in nature, which we directly send to the cloud. We use Amazon Cloud right now, although one can replace this by other cloud providers rather easily. But most of these things, they are listeners set up, which can essentially be able to both manage the data coming in and then be able to then provide data to different users based on their requirements. Obviously, our goal is to be able to store the data in using a file system which is cheap enough, and that's the other part of what we work on, is how do you store IoT data sensibly from a both cost perspective and a processing perspective. So to come back to the intersection, on the intersection, what you have is you have essentially video data, LiDAR. In some cases, you also have other radar data, for example, as was discussed. And then there are these ground sensors. What happens in every intersection pretty much in North America is that on every stop light, there are sensors for every lane, and there are also advanced sensors typically around 100 yards before that, which also have sensors. All they do is they detect presence and absence of a vehicle using loop detectors. Every time a vehicle passes over it, they record that information, and we get that information at a 10 hertz level. From my understanding, similar sensors exist in India also, but they typically are hanging over the road, because obviously digging the road is probably much more difficult there, given that these were probably installed more recently. But again, the whole idea of these sensors is that you're collecting presence and absence of all the vehicles which are passing through the system. Generally, they are not useful in detecting what the size of the vehicle itself was.
I have a question by Mukund.
Sure.
Yeah, hi Sanjay. So we have come across similar data in India across traffic intersections. But one typical problem that we face here is that we are able to identify the intersection name, but the arms of the intersection or the arms of the junctions is something that we are not able to identify from the data itself. So in the ATCS controller, we have different stages of the intersection control, and these stage numbers are essentially interlinked with the arm names. So we'll have to make a correlation from the ATC system in order to identify the arm names. So we would like to understand how this data looks with you.
Yeah.
And
So right now what happens is that we get data from every detector, right? So generally, for example, if there are 3 lanes on the major and 2 lanes on the minor side, so you will get 6 plus 4, 10 lanes, and there will be probably of the order of 20 to 40 detectors, and each of them will get data by the detector number, right? And we have the same problem to some extent, although the detector to phase and the detector to channel mapping, as we call it, is available, or the arm mapping as you're talking about is available, but sometimes it's 10, 20 years old, and there's reconstruction going on all the time. So some of that data information is missing, if you may, right? So we have techniques to be able to figure out which arm a particular detector belongs to, and I'll talk about it a little bit if we have time.
okay, thanks.
I mean, the general idea at a very high level is that if there's a green light on the major phase, you expect more traffic to come on the detectors which are on major phase, right? Similarly, when the light is green for the minor roads, you expect more traffic to pass through those detectors. So we have developed machine learning based system to be able to automatically classify whether it's an advanced detector or a stop bar detector, and whether it's on a major phase or a minor phase.
Okay.
So what we do is we use all these different kinds of data sets and be able to then solve applications which are of interest to the traffic engineers. So we work very closely with them. They define the problems, we solve them, if you may. So for example, for using video data, we have methods to detect near misses, predict Q lengths on the intersection, which is useful for optimization. We can do turn movement counts, how many people are going straight, how many people are taking a right. We can do near misses, we can do trajectory analysis, we can figure out abnormal and unsafe behavior by the hour, by the day, by the week, whatever you want, right? Similarly, we use the ground sensor data for figuring out how bad the intersection is in terms of congestion, in terms of, if the data coming in suddenly it goes down, we can detect traffic interruptions. We use it for computing travel times. And this is the part which you were asking for. How do you figure out the arm? We can look at this data and look at the patterns and automatically figure out whether it belongs to arm 1 or arm 2 or arm 3 or arm 4. So we do a variety of these things. Some of these, the ones in the blue have been already developed and they are being used in the field, if you may. The other ones are still under development and we are working closely with some of the folks. Again, the amount of data which we are getting is large, so we need to have expertise in storage, processing, machine learning, and then be able to then create dashboards which can be useful from a traffic engineer's perspective. So this is an example of what we can do using video. It has a fisheye camera on the right. You can see all the vehicles which are passing in. We process all this data. We map it automatically to a Google Maps to convert from a spherical coordinate to a rectangular coordinate, automatically classify all the vehicles reasonably accurately, and then be able to have tracks available for each of the vehicles. And then we can effectively, what we are doing then is using convolutional neural networks, and we have a specialized network which runs around 40 data is coming around 10 to 20 frames per second, but our GPU's processing happens at 40 frames per second. So we can effectively do most of this in real time with very few frame delays, number of delays, latencies of the order of 4 to 5 frames of data. The other important part is that we care about privacy issues. Like you had mentioned earlier, our goal basically is not to say, hey, whether a particular person or a particular vehicle was there to give a challan or something like that. Our goal is to be able to understand the trajectory behavior of the intersection, on the intersection for different vehicles and pedestrians, so that we convert this data into these tracks frame by frame, and then we use this information in some sense to do further processing. We can even hide the date and the time and the intersection ID if necessary to prevent future misuse. Again, the goal is that you do this in real time, you send this to the cloud processes some of this data at a hourly basis, and after that it may decide to throw that information away in the long run because no longer useful, or keep a succinct information by kind of hiding some of this, so that at the end of the day, no one can then use this data to be able to figure out whether you were there at a particular intersection at a particular time. So we then do studies from that. Like this is one intersection in Orlando. There are two cameras here. We have systems which will map both these cameras onto the same intersection, fuse the information in real time using both video processing and machine learning techniques, and then we have a system which basically collects both of the data, fuses it together. You can see that this is a fused information on the right. It will divide up into the 8 phases which are typically there and see which phases are on and what the traffic movement for that particular phase is. It can then, you can compute all kinds of aggregate statistics, display them on the dashboard itself. These are the turn movement counts for that particular intersection. You can get deeper statistics if you want from that, and then be able to look at and see where the hotspots are in terms of near misses and things of that nature. So what can you use this for? You can do comparative displays and say what's happening for different phases in a particular hour or a particular day of the week. So for example, you can do kind of a weekly trend analysis and say, hey, I'll divide up my data early morning, noon, late afternoon, and evening, and do this for different days of the week. I'm just showing 3 of the 7 days. And what we know that there's a commercial area here where most of the traffic on Sundays does, because these are doctors' offices, no one goes to the doctors on the Sundays because they're closed. So you can use this kind of information to do signal timing, which is based on day of the week and hour of the day kind of analysis. And then you can say, well, I know my traffic patterns very well, so I'll assign my times based on that. You can count risky behavior. You can say how many people took a left turn on a red light, how many people jumped the red light, how many people changed lanes on the red light. And of course, some of these risky behaviors obviously have to be customized to different geographies. So whatever may be risky here may not be defined risky in India, or different locations and different cities may have different definitions. The good part is that since we have the trajectory information, developing these algorithms becomes rather easy at that juncture. You can look at all the vehicle-to-vehicle interaction and say, look, there's a hotspot in this particular area, and you want to then go back and look at the data and see why these vehicles came close to each other. Was it because of the design of the intersection, or can you change signal timing behavior? So for example, there's another example here. There's a lot of, in this particular crossing, this right near the university, a lot of students cross from this side to this side, and when the cars are taking a right turn, they interact with the pedestrians right here, and there have been many accidents because of that. And so this one kind of analyzes that and says, hey, there is a hotspot here. Many times these pedestrians will run and spend some time with this barrier. So there's like another hotspot right there because the vehicles come very close to the pedestrian. So this kind of analysis can then be useful by then figuring out what the countermeasures are. For example, in this case, the countermeasure may be, for example, that if this traffic in this direction is interacting with the traffic on this direction, then you want to be able to say, look, there's a higher chance of accidents, and then you say, look, I'm going to have a protected left so that this traffic cannot interact with that. Now, obviously, that improves safety, but then it reduces throughput, and then the human comes in the picture and say, what level of safety is important enough to reduce throughput, and vice versa. Similarly, in this case, what happens is that you have pedestrians interacting with, which are crossing on these blue markers, interacting with this traffic. And again, what you can do a variety of countermeasures to prevent that from happening by protecting the pedestrian time, if you may. But again, it has an impact on throughput. So the good part about the system is that you can change something, and then next day itself or next hour itself, you can see what impact it had. Clearly, some impacts are going to be measurable based on the hours. Some impacts are going to be measurable based on the day of the week. So if you want to look at what happens on a Monday, then you have to wait for the next Monday to see the impact. The other thing which we want to be able to do is you can see that we are tracking all these pedestrians right here. This guy is J crossing. We want to be able to, detect that as soon as possible, and then be able to warn all these vehicles on the intersection which are connected either through devices in the car or maybe through a smartphone app in the long run, to be able to say, look, there is someone crossing here. So at least all the vehicles which are passing by here may hit this particular pedestrian, and so we can potentially prevent accidents in the future. This is another example of the same thing here. If you look at this pedestrian right here, it's basically crossing as the vehicles are passing by around 30 miles an hour, and the pedestrian will go back and forth, and we want to be able to prevent accidents from happening in this particular case. So part of what we do is we want to be able to predict. So for example, if you observe the red trajectory, the green is what we are predicting and the blue is the actual one. So till the blue and the green are matching, that means we are doing well. And our goal is to be able to predict the location of every object, in particular all the cars and the pedestrians, 3 to 5 seconds before where they're going to be. And if there's a potential for an accident, then we can warn the appropriate entities. Our current latency of processing around 1/10 of a second. We also want to be able to use this data to create anonymous signatures so that we can track vehicles across multiple intersections. So for example, in this case, if all these these vehicles are arriving at intersection 1 and then they go to intersection 2, the same vehicles are generally going to arrive to the next one. Obviously, there is going to be leakage where some vehicles will take a left turn and go away. but for a good fraction of the vehicles, we can know when they arrived at the next intersection. They come with different, the cameras are at different locations, so you can see that the perspectives are different. So we are able to then match these vehicles and then say, look, what was the travel time? And this gives us a very good idea of the travel time distribution on that particular segment. And then you can extrapolate that to get the travel time on the corridor. And then you can use this information at some juncture for more real-time optimization to say, hey, if I change something, did it actually lead to an improvement in my travel time on the corridor? I'll take a break right here, and if there are any other questions, I'm happy to answer them before I move to the next segment of my talk.
I'll say it. So I wanted to check, are these cameras deployed specifically for this purpose, or are these the general purpose surveillance cameras or some other cameras which have been installed on intersections, or are these traffic cameras? Like who has?
So I think these cameras are installed already. We did install, I mean, again, some of this is experimental, but these cameras are already being installed by the city as part of their surveillance. So we are not, adding specialized cameras, if you may, right? Although the processing of the data itself is novel, right?
Yeah, yeah. And okay, so one more question I have is that when you suggest changes in signal timings, like do you suggest for a given, like do you do analysis just for a given intersection, or I mean, I guess it has to be done over a grid, right? Because there will be some kind of a ripple effect of changing signal timings at individual intersections.
I'll come to that in a minute.
Okay.
All right. So now moving to another data set, which is the ground sensor data. The good part about the ground sensor data, as I pointed out, is that a large fraction, maybe around 80–90% of the intersections have these ground sensors, and we can get this data in real time. As I was pointing out, there's a sensor at the stop bar and the advanced bar, generally for the major streets and the minor streets, and we want to be able to effectively, what you get is a waveform like the one on the right? Every time a vehicle passes by, you get a peak. Sometimes multiple vehicles may pass by in the same second or so. So you get these kind of waveforms. And these waveforms are pretty interesting because they capture a lot of information. So for example, if the vehicles are very close to each other when they are driving, then the waveforms, you can find that information using the detector from 9 and 33, for example. You can do gap analysis, you can do all kinds of interesting stuff, and we are developing machine learning algorithms for all of those things. So as I was pointing out, we get data from around 400 or so intersections. And so what we want to be able to do, and this addresses some of the questions which were asked earlier, is ideally what we want to be able to do is create a real-time digital twin where you say, for example, you had a corridor like this is only a part of a network, right? And obviously traffic, if you make changes on one, then the traffic to 2 will change. And if you make changes on 2, the traffic to 3 will change. So you cannot look at these intersections independently, right? Because if you optimize each of them independently, you're screwing up the correlation. Most corridors, the way they are set up at a very simple level is that the cycle time for each of these intersections is roughly the same. And then you say, look, how much time do I assign to green phases, and how do I do a phase offset, as they call it, for these intersections is decided, right? So the problem, unfortunately, is that several parameters need to be optimized. So let's say even there are 10 parameters for each of these intersections in terms of how do you divide up the cycle among the different phases, how much time to give to pedestrians, because the traffic behavior on each of them may be slightly different from each other, right? Because their minor streets have different behaviors. Or in some cases, they may be on a hub where there's a major street on the perpendicular direction also. So let's say there are 10 parameters, then essentially if you were trying to take this data, you'll have to do 10 to the power 4 combinations, and then basically you need to be able to derive these parameters for all of these, including the driving behavior parameters which are part of a simulator. So the challenge basically is that if this digital twin is good enough, then you can say, look, if I make a change on this intersection, I can observe in the digital twin. And if I can observe the data on a digital twin, then obviously I want to be able to then use that for optimization. But if the digital twin is not good enough, then whatever I'm optimizing for, if you may not be very useful because there may be a reality gap. So you want to make sure that there's not much of a reality gap between the twin and the network. And so our goal is to be able to create this digital twin at a corridor and a network level, so that then if I want to make changes, then I can actually observe that in real time or in an hour delay or a day delay, depending on the nature of the twin which you are working with. So one simple way which most people create a digital twin is basically use a simulator, right? So you can create a simulator. What simulator does is it tracks all the vehicles, one vehicle at a time, and based on the signal timing behavior at the intersection, you can create different topologies based on real world topologies. That's easy to do. Those are CAD tools available to do that. But then after that, you need to create infusion of vehicles on this side on all the different segments, and generally people use some kind of a origin destination flow patterns to be able to generate that. The biggest challenge with simulators is that they're very, very slow. So a simulator for 1 hour of data may take of the order of several minutes. And the question is now, if you have 10 to the power 4 or 10 to the power, if you have say 7 intersections on a corridor, now you're talking about 10 to the power 7 parameter combinations. Suddenly things start becoming out of hand, and most simulators are never really used in real time anyway. Even when they're used offline, they are very limited because they don't directly take real traffic into account. Our goal is to be able to say, look, I want to be able to have a simulator which can take real traffic into account. So if I make any changes, I can observe the changes on the simulator, and then they should be reflective of what happens in the real world. So the challenge is, as I said, you can use a microscopic simulator like what I described. The problem basically is that you need to calibrate all these different parameters along with the signal timing parameters, and suddenly the number of combinations can be of the order of thousands to a million. And if each of them takes minutes to an hour of simulation time, then at that juncture, it becomes very slow. So our goal is to basically say, hey, can I replace this microscopic simulator by a deep learning based digital twin, which is at least 1,000 to 10,000 times faster, so that if I can do that for each of these intersections and then going to the corridor and then going to the network, then again, I need to make sure that I measure the reality gap somehow, because if I don't measure the reality gap, all the results which I'll get will be useless. So what we are working on is developing machine learning based algorithm to take the real data which is coming in and be able to use that for both calibration as well as then to be able to say, hey, if I'm predicting something, is the real world data which I'm observing based on what I'm expecting to happen, or something else is happening, that means my models are not good enough. So that is the goal. And the way we generate these twins is by actually generating a large number of millions of simulations. So what we do is basically the real world data is large, but it's not enough because it doesn't have a lot of counterfactuals. So for example, if the real world data is based on a cycle time of 150 seconds with major direction getting 80 seconds and the minor getting the remaining time, then at that juncture, if I don't have data for what happens when if I change it from 80 to 90 or from 80 to 70 or change the cycle time. So we do want to be able to generate that data from a simulator, but still be able to feed real world traffic conditions, if you will. So we have developed these simulators. Our goal basically is long term to be able to develop a real-time AI-based digital twin at the network level. But what we are doing is we are breaking in the problem into first saying that, hey, should we first do it at a corridor, or even first at an intersection, or maybe a hub, which is at a crossroad of two major corridors, if you may. So we have developed these models already at the intersection level. I'm going to present you some results on that. And we are now working on developing it at the corridor level. And then once we move from a corridor, then we can move to the network level. Generally, a network is nothing but a cluster, if you may. In this particular case, a network may be corridor 1, corridor 2, corridor 3, corridor 4. Most cities are if you may, based on this kind of transportation network. Like for example, on an intersection twin, the interesting part is that, as I was pointing out, we are observing data here, we are observing data here, and we are also have data for the signal timing. What we want to be able to do is, by looking at that data, be able to say, hey, what is the egress waveform? And then from there, be able to predict what the waveform for the next intersection is. And this becomes, in the long run, a feedback loop to say, hey, if I can predict this properly, I can observe it. So if my prediction of O based on this A and S is very good, that means my models are working very well. And not only that, what I can do is I can actually use this ANS to predict what the input waveform was to this intersection at a 500 meter or 1,000 meter distance, and then say, what happens if I change the signal timing from whatever it is to something else? Obviously, this is going to be fixed. The only thing which is going to change is then A and S, and if I can predict that, and I can predict the overall, performance measures of this particular intersection, then I can say, look, this is what is happening today. If you change from X to Y, I expect this to happen. So the key part, obviously, for this is to be able to generate lots of real simulator data for a variety of. So we have data sets. We have generated 30 million hours of traffic simulations. The data set itself is around 60 terabytes, then which we use for training our AI models and also testing them, if you may. The way we generate this data is we have a parallel version of the SUMO simulator. We have added ring and barrier, which is the standard implementation, which is not there in SUMO, to make it more practical. And then we run this on a 5,000 core machine to be able to generate 5,000 simulations in parallel. And so effectively, if you run this over months and several months, you start getting data sets of this size. And so what we then do is we develop, for example, an intersection twin, which basically has, I'm not going to go into the details of that. It's based on a recurrent neural network, which has both temporal attention modules as well as a phase attention modules. And then we want to be able to predict the output waveforms. This network has roughly 20,000 parameters. And so the idea basically here is that, hey, this is the actual one and this is the real one. And so we obviously want to be able to do this at a small aggregation levels, this 5 second, 10 second, 15 second. As you can see that as you increase the aggregation levels, from the things start becoming more and more accurate. But generally speaking, we are happy with granularity of around 5 to 10 seconds without any problems. And for that, we are getting reasonably accurate results.
I have a question by Manjunath.
Sure.
Hi, Sanjay. Couple of questions actually. One, yeah, so these waveforms correspond to some kind of a traffic intensity, I would assume, right?
Correct.
So are they just some? Yeah, go ahead. Sorry.
Yeah, go ahead.
Yeah. So are they? I would assume that because you're using the ground sensors, they are essentially some kind of a point processes. Sort of, yeah. I mean, I'm trying to be. So number of points basically are just counts,
correct.
right?
So basically, if you think about it, right, in 5 seconds, generally we see that there are only 1 or 2 vehicles can go over a particular intersection, right? Yeah. So basically, in this case, the y-axis is going to be 0, 1, or 2. If you're looking at 10 seconds, the y-axis is going to be 0, 1, 2, 3, 4.
Yeah,
right?
So it's just a count that what you mean by.
It's just as simple as a count, if you may, right?
Okay. The second question is when you talk about these counterfactuals, the twins essentially. So that is what you're using to generate your counterfactuals, or is that
no?
Is
so
that used for something
the
else
counterfactuals are coming from the simulator, right? So what we do, what I do is I use the because the only observed data which I have available is at the advance and the stop bar, right? Okay.
Right.
So what I do is from there I can impute the I, right? Okay.
Right.
All right. And once I can impute the I, then I can change the signal timing and say what would have happened if I change the signal timing from this, and the A's and the S will change. The only observable points, if you may, are the A's and the S, and then the same A's and the S at the next intersection. Right?
Sure. So then what is the twin being used for?
So the twin basically, look, suppose I have a signal timing plan here, right? Okay.
Right.
All right. For a given traffic condition, let's say that this is an isolated intersection which is away from any other corridor for now, right? Okay.
Right.
Now I want to understand what happens to the performance of this intersection if I change the signal timing plan from ST to ST prime?
Okay.
But remember, I can only observe data here, right? Okay. So unless I know what the I is, because remember, A and S are highly correlated with the signal timing plan, right?
Right.
So I
Right.
can't change the signal timing plan and say, oh, let's keep A and S to be constants, right? The only thing which is constant is I, basically, correct? Which is the
Right,
input
right.
traffic to their intersection, right?
Right. Right.
Okay.
Okay.
So what I do
Okay.
is I use the twin to basically say, hey, what happens is that this twin is able to model this network just like a simulator can, right? So in a simulator, I can just feed in the I values and I will get what happens when I change the signal timing plan from A to B to C, for example, right? Okay.
Yeah. So
All right.
I mean, what is what is it that you are buying through the through the twin that you couldn't get on the simulator? So that's sort of I'm missing
Well, so
that part.
there are three things which I'm buying, right? One is this is 100, this is roughly 10,000 times to 100,000 times faster, right?
Okay. I see.
Because I'm using a deep neural network, so
Got that.
I can get the same result instead of a few minutes, I can get it in a few
Yes.
microseconds,
Okay.
right? One.
Okay.
Second thing is simulators cannot take data at A and S. They can only feed data at I, but I can never
Right.
observe data at I ever, right? Because I don't
Okay.
have any sensor sitting here, right? Okay.
Right.
All right.
Right. Right.
So since the data is only available at A and S, I can't use my existing simulators because they
I
can
see.
only feed the data. So I can actually use this twin to actually impute I and effectively say, look, for this A and S and this signal timing
This will be
plan,
applied.
if I change the signal timing plan from ST to ST prime, what will happen? Right? So neither of those facilities are there in the simulator, right?
Got
Correct?
that. Got that. Okay. Okay.
Right?
Okay.
And
Thanks.
then it makes sense, right? Okay.
Yeah,
All
it
right.
makes it. Yeah. Thanks.
Okay,
So
before I come to Anirudh, there is a question in chat by Hemant, and he's asking in real-time digital twin using AI, which model parameters are updating and whether the gap is dynamic or fixed configured.
yeah, so basically, the what we are doing basically is our goal is to build a twin which will have both the intersection parameters and the driving behavior parameters both included, right? So obviously, the idea is that we want to be able to use the data coming in from the real world both to understand the behavior of the driver, impute the behavior of the driver, if you may, right? In terms of gap analysis, in terms of how many people speed, if you may, on the intersection or between intersections, right? Because none of that data is observable directly. Those are all latent variables, if you may, in most real world situations. So we want to be able to capture those latent variables as precisely as possible.
Okay. And then he had a follow-up. What is the purpose of the advanced detector that you're using in the intersection twin, and whether the signal timing varied in every cycle?
Yeah, so the thing is that generally speaking, again, the current state of the art is that they typically will have the same signal timing plan for multiple hours, right? So they'll divide up the day into three parts: morning, afternoon, evening, right? In most intersections. So they will have the same plan. So that's one of the reasons we want to study and see how can we change this signal timing plan every cycle or every 5 cycles or every 20 cycles, right? Or every 100 cycles, each cycle being roughly between 120 to 180 seconds long. Again, we also understand that, look, theory may say something, but practical applications require you to look at real world constraints where the traffic engineers may not be happy using our system to be less than 1 hour, saying that, look, if you're changing your signal timing plan every hour, that's plenty, right? And maybe that's good enough because you get most bang for your buck, if you may, right? But also remember that today what happens is that they do signal timing plans every 2 to 3 years. So if we can get to doing it once every week, we are already kind of changing the dynamics of what happens today by a large amount. So again, these are in some sense policy issues. Our goal is to be able to say, look, what happens, what is the optimal signal timing plan for a given traffic pattern, whether we derive it for a cycle, or whether we derive it for an hour, or whether we derive it for a day, is something which we can let the policymakers decide.
Thank you, Sanjay. And last question by Anirudh.
Yeah, my question is now if we had a real simulator, I mean not real, old time simulator, then we could change the data the way we wanted. For instance, now we are in COVID times. I want to simulate a condition of pre-COVID time for which I don't have real data, but I could have. But now with a digital twin, if I have data only during COVID times, how will I simulate it for a pre-COVID time traffic? Because that would probably happen again after a few more months.
No, but again, remember, simulators are very powerful tools, right? You can simulate stuff which doesn't even exist, right? So your goal basically is to develop, effectively you're developing a machine. Think of it this way. This is nothing but like a kind of a, if you think about an intersection, what's the intersection, right? All the intersection is doing is moving stuff from one side to the other based on a signal timing plan, correct? Right?
Yes.
So the fact that we are able to generate all kinds of traffic patterns, which with high congestion, low congestion, no congestion, everything possible, right? We feed everything, we generate a variety of such traffic patterns, right? You name it and we can generate it with gaps, without gaps, with gap of 1 meter between cars, with gap of 5 meters between cars. This particular engine doesn't care. All it cares about is what traffic patterns are going to be generated based on those different traffic situation and how this traffic is going to be swapped from this side to the next side, right? Till it learns that dynamics just like a simulator can, then it doesn't really care about that's the advantage, right? That you can feed in any traffic pattern which is in some sense which was not even observed in the last 6 months because we are generating so many of them, if you may. Of
So
course, if your simulator is being fed with very limited amount of data, so for example, if I only fed data for left-hand driving behavior and then I moved it to the US, which has right-hand driving, it probably won't work as effectively, right? So in some sense, obviously these networks are as good as the data which you feed them in, right?
So my question is, in the when you are using digital twins, in that also can we sort of use it to simulate data which is not available in the recordings?
Oh, yeah, completely. So the
We
whole
can.
idea is that
Okay.
how is the digital twin being developed? This is basically nothing but we take the detector logs, we look at the arrival waveforms, feed the arrival waveforms into SUMO. So we are basically using the simulator to generate the data for all possible conditions which we can think of, and then saying, hey, go learn this, basically.
Okay. Next day, first, I wanted to compliment you on excellent presentation. And in case you wish to try it out, to have a field trials in India, I am Chief Security Officer of Electronic City Industrial Township Authority in Bangalore. We have 19 road junctions with traffic signals here, and we have cameras in all of them. So I'm ready to offer our data for you to conduct your field studies in India if you wish to.
Oh, I appreciate that. And obviously, we should have a separate discussion about the practicality of what we are doing in the Indian conditions. Because remember, much of what we have trained this stuff is so far on the US data. And to your earlier question, hey, what changes happen? We do know that driver behavior in India is very different from driver behavior in the US, right? So obviously, we need to be able to capture that in some systematic fashion. But please send me your contact information, Abhay, and I think the other folks should also have my contact information.
Thank you very much.
Thank you. I know I'm out of time, but maybe this is a good time to stop right here. I have a bunch of other things which I can present, but obviously, given the time, if there are any more questions which I can answer, I will be happy to answer them.
I have one question. This is Abhay.
Sure.
So one thing which a little bit bothers me, first of all, it was a great presentation and really great work. But my one question I have is, like initially you were showing the kind of compute storage infrastructure you have put in just for say one or few intersections, right? One thing that bothers me is that how scalable it is. I mean, in terms of, or do you have plans to take learnings from one and extend it to other places, or do you see that for every intersection or for sort of every major intersections you have to put in that kind of infrastructure? Then it becomes a little unscalable in terms of the investments, right? How do we
No, fair. That's a fair point. But look, the cost of a GPU is few $100s at this juncture, right? The cost of a video camera is a few $100s. Obviously, it has to be weather hardened because traffic intersections work 24 hours a day under different conditions. So the cost of this stuff is high, but you can start doing a lot of practical assumptions. You can take so you suppose you have video cameras on 5 intersections, you can combine them together and send it to one box by using simple fiber optics or even 5G in the future. And then at that juncture, let's say you have 1,000 intersections in the city, you can have 100 such small data, I won't call them data centers, but small boxes with 8 to 10 GPUs, which can process the data. And then once they process the data, use another 5G to be able to send it to a central cloud, right? So I think the cost actually compared to the road infrastructure is very, very minimal, right? I mean, imagine to make 1 kilometer of a road will cost you of the order of 100 crores, right? So we're not really talking about a large amount of investment to be able to get the best utilization from the road. Now, again, I'm not trying to suggest that this is cheap, but it's very scalable from a logical architecture point of view. The cost obviously is something which one has to understand based on local conditions.
Sure.
So I guess, I mean, given the time, should we close at this juncture?
Yes, we can. I think I would like to really thank you once again. It was a wonderful talk, and let's hope that we are able to get some of this data, some of the data that you have mentioned. We need to see what kind of data that is coming to IUDX or in the data exchange from various cities, and I think then we can be in touch later also to see if some pilots can be run somewhere with the technology.
Sure, and I would be happy to, provide help as you collect the data itself in, the form and shape which you should for future processing, given that we have been, gone through the cycle a few times where we were storing the data in a particular form and then realized that other formats are much better from a traffic processing perspective.
I think one question on that front, sorry, I have is that
please.
Supposing we don't have road sensors on the intersections and we have video cameras though. This could be some general purpose video cameras. Then what kind of data is that? Like I'm assuming that we can use some kind of analytics to give you the data equivalent of what is coming from road sensors, and then we should be able to feed into the digital twin.
Yeah, completely. So, I mean, in some sense, look, the whole idea here is that different modalities will provide you different quality of information, some better than the other ones, but we don't care really. We divide up in some sense, data collection, data fusion, and optimization as 3 separate stages. And so in some sense, the optimization algorithms don't really care whether the data is coming from video cameras in terms of arrival and departure, or it's coming from ground sensors or some other modality, right? So a lot of these things are stackable and somewhat modular. Now, that doesn't mean that they are perfectly going to be able to swap one from the other, but that's what we try to achieve.
Cool. Okay, then I think thank you very much. With that, I think we will close this session. Again, from all of us, it was a great beginning. And once again, thank you. Good night.
Thanks, good night.
Thank you, Sanjay. Thanks, everyone.
Yeah.